physics. Light. Light. What is light? Light energy is essential to see the wonderful and colorful world around us. Light causes the sensation of vision and helps us to view the objects. Light causes many optical phenomena such as image formation by mirrors, twinkling of stars due to reflection, formation of rainbow due to dispersion of white light. Spherical mirrors. A mirror in which the reflecting surface is curved is called curved mirror. The most common type of curved mirror have spherical shape. Such mirrors are called spherical mirrors. A spherical mirror is a part of a hollow glass sphere with one of its curved surfaces polished in silver while the other acts as a reflecting surface. Concave mirrors. A spherical mirror whose inner surface, curving inwards, is the reflecting surface and the outer surface, bulging outwards, is polished is called a concave mirror.
Convex mirrors. A spherical mirror whose outer surface is the reflecting surface and the inner surface is polished is called a convex mirror. Terms related to spherical mirrors. Pole. The geometrical center of the spherical mirror is called the pole of the mirror. It is denoted by P. Center of curvature. The geometrical center of the hollow sphere of which the spherical mirror is a part is called its center of curvature. It is denoted by C. Principal axis. The straight line passing through the pole and the center of curvature of the spherical mirror is called principal axis. It is represented by Px. Radius of curvature. The radius of the hollow sphere of which the spherical mirror is a part is called the radius of curvature of the mirror. It is denoted by R. Principal focus or focal point. The point on the principal axis where all rays of light parallel to the principal axis meet or appear to meet after reflection is called the principal focus of a spherical mirror. It is denoted by F. Converging mirror. In a concave mirror, all rays of light parallel to the principal axis converge after reflection and meet at the principal focus. Due to this property, concave mirrors are also known as converging mirrors.
Diverging mirror. In a convex mirror, all rays of light parallel to the principal axis diverge after reflection, and appear to come from the principal focus. Due to this property, convex mirrors are also known as diverging mirror. Focal length. The distance between the pole and the principal focus is called the focal length of the spherical mirror. It is denoted by F. Focal length of a spherical mirror, concave or convex, is always half of the radius of curvature F equals R dou or R equals dou F.
Aperture. The area of the mirror from which reflection takes place is called its aperture. It basically denotes the size of the mirror. Linear aperture. The length of the straight line joining two opposite extreme points on the periphery of a spherical mirror is called its linear aperture, denoted by the straight line mm. Angular aperture, the angle subtended by the two opposite extreme points on the periphery of a spherical mirror at the center of curvature is called its angular aperture, denoted by angle MCM. Angular aperture, the angle subtended by the two opposite extreme points on the periphery of a spherical mirror at the center of curvature is called its angular aperture, denoted by angle MCM. Angular
Real and virtual images. Point of image formation. For the formation of the image of an object, the corresponding reflected rays should either actually meet or appear to meet at a point. This point is known as the point of image formation. Real image. The image formed due to actual meeting of the reflected rays at a point is called a real image. Virtual image, on the other hand, the image formed when reflected rays only appear to meet at a point but don't actually meet is called a virtual image. Difference between real and virtual image. Ray diagrams. The image formed by a plane mirror is erect, virtual, and is of the same size as that of the object. But the nature and size of the images formed by spherical mirrors depend on the nature of the mirror, distance of the object from the pole of the mirror, and focal length of the mirror. The exact nature and size of the images formed by the objects kept at different positions in front of a spherical mirror can be determined by tracing the path of light by drawing simple diagrams. Such diagrams are called ray diagrams. In a ray diagram, the object is represented by a vertical arrow. For simplicity, it is kept perpendicular to the axis such that its foot touches the principal axis. Construction of images using ray diagrams. One. An incident ray passing through the center of curvature. An incident ray passing through the center of curvature of a concave mirror reflects back along the same path, without any deviation. In case of a convex mirror, an incident ray which appears to move towards the center of curvature is reflected back along the same path without any deviation. An incident ray parallel to the principal axis. In case of a concave mirror, an incident ray parallel to the principal axis passes through its focus after reflection. In case of a convex mirror, the incident ray after reflection appears to come from the focus of the mirror. An incident ray passing through the focus. In a concave mirror, an incident ray passing through the focus is reflected parallel to the principal axis. In case of a convex mirror, the incident ray, which appears to move in the direction of the focus of the mirror, is reflected parallel to the principal axis. A ray of light incident at the pole of the mirror. In a concave mirror, a ray of light incident at the pole gets reflected along a path such that the angle of incidence is equal to the angle of reflection. This is also true for a convex mirror. Images formed by a concave mirror. The image formation by a concave mirror and the ray diagram for different positions of the object are explained below. When the object is at infinity. When an object is at infinity or very far away, the rays coming it are considered to be parallel to each other. Consider two parallel rays coming from a distant source, one striking the mirror at its pole and the other passing through its center of curvature. The ray incident at the pole reflects at the same angle, obeying the first law of reflection. The other ray will retrace its path after reflection. The two reflected rays intersect each other below the principal focus. So, the image AB is formed at the focus and is real, inverted and highly diminished. When the object is beyond the center of curvature, the ray parallel to the principal axis passes through the focus of the mirror after reflection. The incident ray passing through the principal focus of the mirror is reflected parallel to the principal axis. The two reflected rays meet at a point between F and C. The image AB is formed between F and C and is real, inverted and diminished. When the object is placed at the center of curvature, the ray parallel to the principal axis passes through the focus after reflection, and the incident ray passing through the principal focus is reflected parallel to the principal axis. The two reflected rays meet at C, so the image AB is formed at C and is real, inverted and of the same size as that of the object. When the object is placed between C and F, let us consider a ray of light coming from the object parallel to the principal axis while another one passing through the focus. In such a case, the image AB is formed beyond C and is real, inverted and enlarged. When the object is placed at the focus, an incident ray parallel to the principal axis of the mirror and another passing through the center of curvature, the two reflected rays go parallel to each other and meet at infinity. Since the reflected rays meet at infinity, the image is real, inverted and highly enlarged. When the object is placed between P and F, an incident ray parallel to the principal axis of the mirror and another passing through the center of curvature. In this case, the two reflected rays do not meet in front of the mirror. They appear to meet behind the mirror when extended backwards. Thus, the image AB formed is a virtual, erect and enlarged. Image is formed by a convex mirror. An incident ray that is parallel to the principal axis appears to be reflected back from the principal focus of the mirror. Another incident ray that appears to pass through the center of curvature of the mirror retraces its path after reflection without any deviation. The two reflected rays appear to meet behind the mirror when extended backwards. The image AB formed by a convex mirror is always virtual, erect, diminished and formed between F and P, irrespective of the position of the object with respect to the mirror. Uses of spherical mirrors. Concave mirrors. Concave mirrors are used in solar heaters to concentrate sun rays towards the food in the container to be heated. They are used as reflectors in headlights of automobiles, in searchlights, in floodlights and in torches. When the bulb is placed between the focus and the pole as in a floodlight, a divergent beam of light is obtained that can spread over a large area. But if the bulb is placed at the focus of the concave reflector as in case of a torch and the headlights of a car, a powerful beam of parallel light is obtained. They are used by dentists to see an enlarged image of a tooth and other areas in mouth. Concave mirrors are used by doctors to focus light and magnify images of small internal body parts, such as the inside of the ear and nose. They are used as shaving mirrors. Concave mirrors are also used in reflector-type telescopes. Convex mirrors. Convex mirrors are used as street light reflectors since they can diverge rays over a large area. As convex mirrors always form an erect and diminished image, therefore, they are used as rear-view mirrors in vehicles to get a wider view of the vehicles coming behind. They are used as vigilance mirrors in departmental stores, malls and offices.